In the first part of this problem, we are going to find the relationship for the force on the object in the hypothetical hole. So we need to calculate F of R. The force on the object of mass m at a distance r from the center of the earth in the hypothetical hole is written as F of R is equals to F of R is equals to mass times of the acceleration, that is g of r. Now by inserting the expression of the g of r into this equation, we can write it as m g naught into small r divided by capital R E. Here this g naught is the gravitational acceleration on the surface of earth, and this R E is the radius of earth. Now we can write the Newton's second law as F is equals to ma. So using this equation number 1 and equation number 2, we can write here ma is equals to m g naught into small r divided by capital R E. So from here we can write this equation as m d square r divided by dt square is equals to m g naught small r divided by capital R E. So from here we can write this equation as d square small r divided by dt square is equals to g naught divided by capital R E multiplied by small r. So this is the required relation. Let's call it equation number A. In part B of this problem, we are asked to find an expression for the period of the oscillations. So in part B, we have to derive a relationship for capital T. The simple harmonic motion can be described by the equation A is equals to omega square x. So this will be our equation number 3. Now by making comparison of this equation number A with equation number 3, we can write here this omega square should be equals to this should be equals to g naught divided by r, capital R E. So from here we can write the relation for this omega as omega is equals to square root of g naught divided by capital R E. Now we can write the period as t is equals to 2 pi divided by omega. So from here we can write this capital T is equals to 2 pi square root of Re divided by g naught. So this is the required relationship for the period of the oscillations of the particle in the hypothetical hole. Let's call it equation number B. In part C of this problem, we have to find a numerical value for this period. So we need to calculate T. Let's put the values into this equation number B. So we can write equation number B as T is equals to 2 into 3.14 square root of Re, which is equals to 6.37 multiplied by 10 raised power 6 meter divided by g naught, which is equals to 9.80 multiplied by 10 raised power 0 meter per second square. So from here we can write the value for this capital T as capital T is equals to 5.06 multiplied by 10 raised power 3 seconds. Or this can be written as capital T is equals to 5.06 multiplied by 10 raised power 3 seconds divided by 3.6 multiplied by 10 raised power 3 seconds per hour. So from here we can write the value for this capital T as capital T is equals to 1.41 hours. So this is the period of the oscillations of the particle which is inside the hypothetical hole. Now let's calculate the period of the low Earth orbits. Let's write the equation for this period. So it will be T low Earth orbits LEO. This is equals to 2 pi square root of Re cube divided by capital G me. Here this capital G is the gravitational constant universal gravitation constant, and this me is the mass of the Earth. Let's put the values into this equation. So we can write here T Leo is equals to 2 into 3.14 square root of RE, which is equals to 6.37 multiplied by 10 raised power 6 meter whole raised power 3 divided by this G, which is equals to 6.67 multiplied by 10 raised power minus 11 Newton meter square per kg square into the mass of the Earth, which is equals to 5.97 multiplied by 10 raised power 24 kg. And we have the square root up to this point. So from here we can write the period for this low Earth orbits as T Leo is equals to 1.41 hours. So from the results of equation number B and this equation number C, we can say that the oscillations of the particle in the hypothetical hole is same as the period of the oscillations of the low Earth orbits. So we can say that this capital T is equals to T Leo. Thank you.